In this video, we're going to do an introduction to differential equations, and this is actually going to cover two different sections in the book, 8.1 and 8.2. So what is a differential equation? Well, let's just first of all come up with an example. Okay, so find a function y that has the property that y prime is equal to y. Okay, so this is an example of a differential equation. We're trying to find a function y that has the property, if we take the derivative of y, we get y itself. Or in other words, we want dy dx to be y. Okay, well notice e to the x works, right? Y equals e to the x. But also y equals 5e to the x works, right? If you take the derivative of 5e to the x, you get 5e to the x. In fact, y equals any constant times e to the x will work for any constant c, and this is called the general solution. Notice, by the way, that y equals 0 will also work, right? The 0 function has the property that if you take the derivative, you get the original function back, but notice that case happens when c is 0. Okay, so this is what's called the general solution of this differential equation. All solutions of this, believe it or not, have this form here. Okay, now what about another example? What if we want y double prime to equal negative y? Okay, or in other words, d squared y dx squared, we want that to equal negative y. Well, can you think of a function off the top of your head that will do this? Well, it turns out that sine of x works, right? If you take the derivative of sine, you get cosine. But then if you take another derivative, you get negative sine, right? So the second derivative of sine ends up being negative sine, right? So two derivatives of y end up giving us negative y. By the way, that also works for cosine, because if you take two derivatives of cosine, you get negative cosine, right? One derivative gives you negative sine, and the derivative of negative sine would be negative cosine, right? So two derivatives, you get the negative of itself. Now, it turns out that any solution of this differential equation is going to have the form some constant times sine of x plus some constant times cosine of x. Okay, like 5 sine of x plus 3 cosine of x, that would also have the property that if you took two derivatives, you get the negative of that. Okay, and so again, this is what's called the general solution of this differential equation. Okay, so a differential equation, here's the kind of technical definition. It's an equation involving one or more derivatives of an unknown function. Okay, and the order of a differential equation is the order of the highest derivative it contains. So if it has a y double prime, then it would be of order 2, as long as it didn't have a y triple prime or something like that. Okay, so let's look at a few examples here. So this first differential equation says dy dx minus 4xy equals 3x to the fifth. So this is a differential equation because you're trying to find a function y, or y of x, that has the property that if you take the derivative of that function, and then you do minus 4x times the original function, you get 3x to the fifth. Okay, now this would be a first order differential equation because we have a derivative of order 1 and we don't have any higher order derivatives. We just have a y prime or a dy dx. Okay, and notice you could write this as dy dx, or you could write it as in the prime type of notation here. Now this second one says y double prime plus 2x y prime minus e to the x equals 0. This would be a differential equation. So you'd need to find a function y that has the property that if you took two derivatives of y plus 2x times the first derivative of y minus e to the x, you get 0. This would be a second order differential equation. We have a y double prime. Now these y's would be functions of x here because we have this. We'll look at cases where sometimes the function y might be a function of time or something, so we might use the letter t. Okay, now here's a third order differential equation, right? The highest, we're trying to find this function y that has this property that if we plug in y here, dy dx there, d squared y dx squared, and d cubed y dx cubed, right? Y triple prime here, we get a true statement. Okay, here's a first order derivative. You might think, oh, that's a third order derivative, but notice this is not y triple prime, this is just y prime, okay, being cubed. Okay, so the highest order derivative we have is y prime, right? So it's derivative order 1. Okay, and this last one, we would think of this y would be a function of t. So we need to write y, some function of t. We need to find a function of t that has the property if you take two derivatives minus one derivative of it, you get cosine of t, right? So this would be a second order differential equation. Okay, now a function y, or y of x, is called a solution of a differential equation if the equation is satisfied when y and its derivatives are substituted into the equation. So let's look at an example. So check that y equals e to the 5x is a solution of this differential equation. Okay, so notice into this formula we're going to have to plug in y. We're also going to have to plug in dy dx. Okay, so y, remember, was e to the 5x. dy dx would be e to the 5x times 5, right? Or 5 e to the 5x. So if we plug these things in here, so for dy dx, we're going to plug in 5 e to the 5x minus 4 times y, but y was e to the 5x. Well, notice 5 e to the 5x minus 4 e to the 5x is going to be 1 e to the 5x, right? 5 minus 4 times e to the 5. But 1 e to the 5x is just e to the 5x, and that's what we have on the right-hand side. So that really was a solution. Now, I didn't tell you how I found the solution. Okay, that's a whole nother story. Like, how do you solve a differential equation? That's another story. I'm just trying to show here that this really is a solution. Okay, now it turns out that differential equations have lots of real-world applications. So anytime you're talking about rates of change, well, you're really talking about derivatives, right? So differential equations tend to be lurking in the background. So there's lots of real-world practical applications. It's one of the things that's kind of crazy is in Calculus 2 here, our class has to do a lot with all these integration techniques, and you might think, what's the point of this? What's the point of integration by parts or improper integrals or trig substitutions? What kind of real world applications do these things have? Well, it turns out that a class in differential equations has lots and lots and lots of real world applications, and you really need to know all these techniques of integration in order to solve these types of differential equations. Okay, so let me give you kind of a real world application that I thought of. So I remember as a kid taking a bath in a bathtub, and after a certain amount of time, the water had kind of cooled off enough that it starts getting cold, right? So maybe you want the temperature to be 100 degrees, but it's cooled off to 84 degrees. And so, one of the things that you could do is just add hot water, right? So let me just turn on the water, add some more hot water to it. The problem is the water level rises, right? And so the water starts spilling out over the top or something. And so maybe another thing you could do would just be to drain out all the water and just put in new bath water. But, nobody ever thinks to do that, right? So, you probably waste a lot of water doing it that way. So one thing that you could do is turn on the water and let the water drain out as well at the bottom. So turn on the hot water, okay, come in maybe 130 degrees, the hot water, and let the water that's, open up the drain so that water drains out. And so it's possible that the water's coming in at the same rate it's leaving. Now, that's not likely. It could be that it's either coming in faster than it's draining out the bottom or vice versa. But just for kind of simplicity, suppose you have a situation where the water's coming in at, say, 6 gallons per minute, and it's also going out the drain at a rate of 6 gallons per minute. And let's suppose that the water is kind of well mixed, so that at one side of the bathtub, it's not any hotter or colder than the other side of the bathtub. And let's suppose there's exactly 40 gallons of water in the tub. So there will always be 40 gallons because you have 6 gallons per minute going in, and it'll also be leaving the tank at a rate of 6 gallons per minute. So there's 40 gallons of water in the bathtub. So you might wonder, well, how long am I going to need to turn on this water until the water temperature gets from 84 degrees back up to 100 degrees, right? So you're talking about rates of change, right? So you could set up a differential equation to help you solve this problem, right? The water's coming in at a certain rate, leaving at a certain rate. How fast is that water temperature changing? In fact, I've kind of actually did set up a differential equation and solved it for this very problem just a minute ago here. And so I found the solution here is along this curve. So notice that time t equals 0. So this would be time here, and this would be temperature. At time t equals 0, it's 84 degrees, right? And we're adding in this water rate of, or at a rate of 6 gallons per minute. It's exiting the tub at a rate of 6 gallons per minute as well, draining out at that rate. And you want to model the temperature. So maybe after 1 minute, so you can look along the curve here, after 1 minute, okay, we are right over here at about 90 degrees, right? After 2 minutes, this is the temperature. So it looks like it's close to 3 minutes here, maybe about 2.9 minutes or so. You're right at 100 degrees, right? And notice over time, the temperature goes up. Now notice the temperature will never go above 130 degrees, right? Now why is that? Well, that's the temperature that the water is coming in at, right? The temperature of the tub's never going to be higher than the temperature that it's coming in at. Now we've made a couple assumptions to kind of simplify things. So we're kind of assuming almost that the water is well insulated in the sense that, heat is not coming out from the water into the air, or vice versa. And so now that's obviously not a great assumption because the water had cooled off initially to 84 degrees. But under these kind of ideal circumstances here, and they're not two crazy assumptions. Okay, one is that the water's coming in at the same rate the water's leaving. We end up getting, in fact, I solved the differential equation, and this was the temperature at time t was this. So notice when little t is 0, we are at, well, 130 minus 46 degrees, right? 46 times 1, so that'd be 84 degrees, right? And you can figure out the temperature at any time t. Okay, well, that was kind of a silly little example, but you can see that differential equations have lots and lots of real-world applications. Okay, now I didn't actually give you the differential equation that I used to solve to get that solution, but it turns out it's a fairly simple situation to model. Okay, now let's talk about initial value problems. Okay, so what is an initial value problem? We'll see that in just a second, but solve the following differential equation. Okay, we have dy dx equals 2x minus 3. Now this is a very simple differential equation because the right-hand side doesn't have any y's, right? It's just dy dx equals some function of x. Okay, so it's actually going to be simple to solve because all we're going to do is take the integral of both sides. What we're going to get is, if we take the integral of the left side, will just be y, and then we can integrate the right side. Now this is going to be subject to the condition that y of 5 is equal to 17. Now this does not mean y times 5, this is y of 5. So we're going to think of y as being a function of x, right? Y of x, kind of like f of x. And this condition here is what's called an initial condition, or an IC. Okay, so what it means is we want to find the function y, not only that has the property that dy dx is 2x minus 3, but we also want to have the property that y of 5 is 17. So if you plug in 5 for x, you'll get 17 as an output for y. Okay, so to solve this, notice that y is going to be x squared minus 3x plus c. Right? So we just have done the integral of the right-hand side. Now this is called the general solution of this differential equation. Okay, but we need to find the specific solution that satisfies the initial condition that y of 5 is 17. So in other words, what we need to do is find the c that works. Okay, so this initial condition, y of 5 equals 17, is going to help us find what that c is. Okay, so we could rewrite this equation, by the way, as not just y equals the right-hand side, but y of x equals that. Okay, so what we want is y of 5 to be 17. So if we plug in 5 for x, we get 25 minus 15 plus c. And so that's really 10 plus c. But we want that 10 plus c to be 17, so c is 7. So our solution is just going to be this right here, where we plug in 7 for c. Right? So this is our solution. So notice you can check that this function, okay, y, or y of x. By the way, you don't have to write y of x. You could write as just y equals this. It satisfies the property that if you take the derivative, right, if you take dy dx, you get 2x minus 3. Right? It satisfies this differential equation, but it also satisfies the initial condition that if you plug in 5 for x, you get 17 as your output, right? The y will be 17. Okay, so this is an example of what's called an initial value problem, or an IVP. So an initial value problem is just a differential equation, okay, a DE, along with an initial condition, right, an IC. Okay, so an initial value problem, an IV, is just a differential equation along with an initial condition. Okay, now we're going to look at a specific type of differential equation here. Now, a lot of times if you're trying to solve a differential equation, it can be very, very hard to solve unless the problem is kind of rigged up in some nice way. Kind of like integrals. If you just write down some random integral, sometimes it's hard to do unless the integral is rigged up in a certain way. Well, it turns out there's a certain type of differential equation, what are called separable differential equations, that have a fairly simple method that you can use to solve them. Okay, now a first order differential equation is said to be separable if it can be written in the form dy dx equals some function of x times some function of y, right? Some g of x times h of y for some functions g and h. Okay, so which of these functions are separable? Okay, now dy dx or which of these differential equations are separable? So we have dy dx equals x cubed times sine of y. Now notice this is a function of x, right? X cubed times a function of y, sine of y. So this is a very simple example of a separable differential equation. Okay, now what about this one? It doesn't look like it's separable. It doesn't look like it's in the right form. But notice if we add x over 5y to both sides, we get dy dx equals x over 5y. But we could write x over 5y as x times 1 over y. So we could write it as dy dx equals some function of x, namely x, times some function of y, namely 1 over 5y. Okay, so this is separable as well. Now this next one is not separable. There's no way to write this as some function of x times some function of y. Okay, so try it. Think of it. Can I write this as some function of x times some function of y? Turns out you can't. So this one's not separable. Same thing right here. Ln of x plus y. By the way, this is not the same thing as ln of x times ln of y, right? That's not the way the product rule or product property of logarithms works, right? There's no way to write this as some function of x times some function of y. Okay, now what about the next one? It kind of looks like it's not separable, but notice both terms have a y, so we could factor out the y and write this as y times the quantity 1 plus x, right? Or in other words, 1 plus x times y, right? So we have some function of x, 1 plus x, times some function of y, y. So this one is separable. Okay, so these first two were separable. These next two were not separable. This one is separable. Now what about the last one here? This is the last one we're going to look at. Is this separable? Well, notice we have a function of x over here and a function of y right there. Notice that the x's and y's are kind of separated, and that's sort of a hint here maybe. But it turns out this one is separable because we could multiply both sides by 1 over y cubed. Or in other words, divide both sides by y cubed. But think about it as multiplying both sides by 1 over y cubed. We'd have dy dx equals the right-hand side, right? X squared plus e to the x times 1 over y cubed. Right, so in other words, we'd have dy dx equals some function of x, namely x squared plus e to the x, times some function of y, namely 1 over y cubed. Okay, so this is a separable differential equation. So these last two are separable, the middle two were not separable, and the first two were separable. Okay, now again, what's the point of separable differential equations? Well, it turns out they're nice because, again, there's this simple method that we can use to solve them. So let's solve this differential equation. We have dy dx equals negative 4x times y squared. Now notice this is separable because it's some function of x, negative 4x, times some function of y, y squared. Okay, so the idea is what you're going to do is separate the functions. So you're going to divide both sides by the function of y. Okay, so that you get the x's on the right side and the y's on the left side. So we're going to divide both sides by y squared or multiply by 1 over y squared. So the left side is 1 over y squared dy dx equals negative 4x. Now, it turns out what you can do in the next step is you can think of the dy dx as being a fraction, right? Like dy over dx, and multiply both sides of this equation by dx. Okay, so notice the right-hand side would be minus 4x dx. The left side would just be 1 over y squared dy, because the dx times the dx, that's going to, or dx over dx, that's going to go away. Right, now this might look a little strange here. We have a dy and a dx here. But in fact, anytime you see something with a dy dx, you tend to think of integrals. In fact, that's exactly what we're going to do is if these two things are equal, then the integral of this should equal the integral of this. Okay, so once we're at this step, so once we've separated the y's and x's, then we bring the dx over to the right side, then we integrate both sides. Okay, now on the right hand side we have the integral of negative 4x dx. That's going to be negative 4x squared over 2 plus c. And the right hand side we have the integral of y to the negative 2. And the integral of y to the negative 2 is y to the negative 1 over negative 1. Now we don't need to put a plus c there. So you only have to put a constant on one side because you could put a plus c there and a plus d on this side. But they can combine into a single constant. So you only need the plus c on one side. Okay, now in other words, another way of writing the left side is negative 1 over y. So equals negative 2x squared plus c. And then you could multiply both sides by y and then divide both sides by this and then take a negative, or just think of it as taking a reciprocal of both sides and then taking a negative. It turns out that y will be 1 over 2x squared minus c. So it's just algebra to get from here to here. So this is a solution of this differential equation. Now how could you check that? Well, you could take the derivative, find the dy dx, and then you could square that function right here and multiply by negative 4x and check, is the derivative the same thing as if you did negative 4x times this function squared? And it turns out it will be. Okay, so for any value of c, this is going to be a solution of this. Okay, now let's suppose we want to turn this into an initial value problem. So not just a differential equation, but a differential equation with an initial condition. So we want y of 0 to be 1. So in other words, when we plug in 0 for x, we get 1 for y. Okay, so we could rewrite this, this right here. So by the way, this is the same differential equation that we had up here. So we get the same general solution. Okay, I'm not going to redo that, but we get this. Now, if we plug in 0 for x, and by the way, I've written it as y of x here. You don't have to do that, but y of x equals this. So y of 0 equals what? Well, it turns out it's negative 1 over c if you plug in 0 for x. But we want y of 0 to be 1, so we want negative 1 over c to equal 1, right? Y of 0 has to be 1. But if we plug in y of 0 here, we get negative 1 over c. So negative 1 over c has to be 1. So c ends up being negative 1. So our solution is going to be y of x equals 1 over 2x squared minus a negative 1, right? Because c was negative 1. Or in other words, y equals 1 over 2x squared plus 1. Okay, that's our solution. Now, how could you check your answer? Well, again, go back to this differential equation. Check to see, does it satisfy this? So you'd have to take the derivative here. So using the quotient rule, or I guess you could use the chain rule or whatever. And you could also square the function right here and multiply that squared function by negative 4x and see, do you get the same thing on the left side as the right side? And you should. And also check to see it satisfies the initial condition. This is pretty easy to check. If you plug in 0 for x, what does this become? Well, it becomes 1, right? Because we get 1 over 0 plus 1. Okay, now how can we solve this initial value problem? Okay, we have 4y minus cosine y times dy dx minus 3x squared equals 0. Okay, and also we want y of 0 to be 0. So this is our initial condition. Okay, so what we have is 4y minus cosine of y times dy dx equals 3x squared. So I've just added 3x squared to both sides. Now, again, the next step, and you always do this with separable differential equations, you multiply both sides by the dx. Okay, and it might seem weird to do that, but you can, there's a way of justifying this. Okay, and the ultimate way of justifying is that it works in the end. Okay, but notice the right side would be 3x squared dx. The right side would be 4y minus cosine of y dy. Okay, now again, once you're at this stage where you have the dy and the dx there, we just integrate both sides. Now the integral of the right-hand side is pretty simple. It's just x cubed plus c. The integral of the left side is also pretty simple. The integral of 4y would be, it'd be 4y squared over 2, or in other words, 2y squared. And the integral of cosine is positive sine, but we have a negative out front. So the integral of minus cosine of y is going to be minus sine of y. Okay, and this is actually a solution of your differential equation, but it's kind of defined implicitly. Okay, there's no real nice way of solving this for y and just writing y equals some function of x. But this will still be considered the solution of that differential equation. So we can just leave it the way it is. Okay, but now we also want it to satisfy the initial condition. So in other words, when x is 0, we want y to be 0. Okay, so our input 0, we want our output to be 0. So if we can plug in 0 for y and 0 for x, we can figure out what c is. Well, it turns out if we do that, we get 2 times 0 squared minus sine of 0. So that's going to be 0 minus 0 equals 0 cubed plus c. So basically you're getting 0 is equal to c. Okay, so c equals 0 is what's going to solve our initial condition. So we just rewrite this with a 0 there. So it basically just disappears. So this is the solution of that original initial value problem. Now, if you wanted to check your answer, how would you find dy dx? Well, to find dy dx, you'd have to do implicit differentiation, right? Differentiate both sides with respect to x. But on the left side, like differentiating 2y squared would be 4y times dy dx. And then to differentiate sine of y, you get cosine of y times dy dx. Now, the derivative of x cubed would just be 3x squared. Okay, but you could do that and solve it implicitly, do implicit differentiation, and check to see that it really does satisfy this differential equation. And it's pretty easy to check that it satisfies the initial condition as well, right? If x is 0, y is 0, that works. Okay, now one last thing, example, find a curve in the xy plane. So find some curve in the xy plane that passes through the point 0, 3, and whose tangent line at a point xy on the curve is 2x over y squared. So we want to find some curve that goes through the point 0, 3, and that at any point along the curve, okay, so if you have some point, let's say 5, 7 that's on the curve, well, what we'd want to have is that the tangent line at that point 5, 7 would be 10 over 49. It would have a slope of 10 over 49. And by the way, I probably said this a little bit wrong. I should say whose tangent line at a point on the curve has slope 2x over y squared. I don't want to say the tangent line is this. What I want is that at any point on the curve, the slope of the tangent line is 2x over y squared. Okay, so if you had a curve that goes through 0, 3, and at any point along the curve, you want the slope to be 2x over y squared. So again, if the point 5, 7 is on the curve, the slope at the point 5 comma 7 would be 10 over 49. So the curve would have a slope of 10/49 as it's going through 5, 7. So again, I worded this a little bit wrong, but whose tangent line at a point on the curve has slope this. Okay, so remember the slope of the tangent line though is just the derivative, right? In other words, we want to solve this initial value problem. We want dy dx to be 2x over y squared. Okay, and we want y of 0 to be 3, because we want, if we plug in 0 for x, we get 3 for y. In other words, 0 comma 3 is a point on the curve. Okay, so how do we solve this differential equation? Dy dx equals 2x over y squared. Okay, well, it's a separable differential equation because we could think of it as 2x times 1 over y squared. So basically we can multiply both sides by y squared, then multiply both sides by dx, and we get y squared dy equals 2x dx. Right, so you see what we did there, just multiply both sides by y squared, multiply by dx. Okay, well then again, we're going to do the integral of both sides. So the integral of the left side will be 1/3 y cubed. The integral of 2x will be x squared, and we have to put a plus c on one side or the other, so let's just put plus c right here. So multiplying both sides by 3, we get y cubed equals 3x squared plus 3c. But notice I don't have to write 3c because 3c is just a constant, and so you can just relabel it as c here. Okay, and finally, y will be the cube root of this. Now, it's important that the c is actually underneath the root here. If we're plus c out here, that would actually not work. Okay, it would not work. Okay, the c does need to be under the cube root. So y is the cube root of 3x squared plus c. Okay, now this is the general solution. So 3x squared plus c raised to the 1/3 power. That's the general solution of this differential equation. Okay, now we also want to find the specific solution that satisfies this initial condition. So in other words, we want to find the c. Okay, so we want, if x is 0, y is 3. So plug in 0 for x. And then notice I haven't even written it as y of x. I'm just leaving it as y. So, but we're going to plug in 3 for y and 0 for x. And notice this is what we get. Okay, we end up getting 3 is equal to the cube root of c. And so c ends up being 27. You can cube both sides and you get c equals 27. So when we plug in 27 for c, we get this. Okay, so this is a curve, right? You could draw this curve in the xy plane. Maybe I'll do that in Desmos in a second here. And this curve goes through the point 0, 3, and it has the property that any point along the curve, the slope of the tangent line is this. Okay, so I've drawn the graph in Desmos. So notice we have y equals the cube root. So I've raised it to the 1/3 power. It's the same thing as a cube root of 3x squared plus 27. So notice we have this curve. Okay, notice it does go through the point 0, 3, but also any point along the curve. You could look at the x coordinate and the y coordinate. If you're to look at the slope of the tangent line there, okay, the slope of the tangent line there would have the property that it would be 2 times the x coordinate divided by the y coordinate squared, right? Wasn't that our differential equation? The slope of the tangent line at any point xy would be 2x over y squared. So the points on the curve here aren't going to satisfy that, but the slope of the tangent line there. So you wonder what's the slope? So the slope of the tangent line here would have the it certainly looks like it would be a negative slope, right? It would have the property that it would be negative. Well, it'd be 2 times negative 1.86 over 3.3344 squared, right? Whatever that number is, that would be the slope of the tangent line there. So here's a curve that has those properties, and notice it satisfies the initial condition that 0, 3 is on the curve. Okay, so this is the topic of differential equations. Again, this is a very big topic. There's a whole class called differential equations. And that is a very practical class. And again, you might think of calculus too as, what are we going to use all these integration techniques for? What kind of use could they be in terms of real world applications? Well, in that class, you'll really see lots of real world applications. So if you go ahead and take differential equations, I would encourage you to do that. You'll see lots of really interesting applications. But this is as far as we're going to get in this class.